Good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or stations further east. As you see, I'm wearing my fetching but classy, tasteful perhaps, Christmas combo. It was a toss-up between this one and my Clark Griswold hockey jersey, but my wife recommended this was the one to wear. But thank you for joining this, the 37th of our regular series of short courses on pumping topics. This one will last about 40 minutes, allowing us time for a Q&A at the end. As in previous sessions, we're trying to maintain educational content rather than product placement. So I've tried to talk about BB5 pumps generically rather than specifically. We believe this is very important in the new world order of many engineers working from home, making in-workplace training that much more difficult. As usual, I include a few slides at the end of the presentation to remind you of who we are and what we do, but I don't dwell on them. They'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. Now just restart the screen share. Yep, there we go. Well, here is a listing of the previous short courses that we've run in the last 3 years. If you've missed any of them, you can get a copy of the materials by following this link to ruhrpumpen.com, to our website, and follow the link to RP Short Courses. If you go to ruhrpumpen.com, you get to this screen, and here is the link to RP Short Courses. Click on that, and it takes you to this screen, where you'll see all of the recent courses listed. Shown here are the latest four, or four of the more recent ones anyway. And you can click on any of them to see the course material and download copies for viewing at your leisure. I recently requested some data on the number of downloads we've had for these sessions, and I was very gratified to see these numbers. Some 10,000 downloads for some of the earlier sessions that have been out there on the website for quite a while. Anyway, this seminar is going to look specifically at double case barrel pumps, API Type BB5, but I'm going to spend a little time looking at why and when you need them, and at what the alternatives are. You'll also see lots of examples of such packages at the end of the presentation. As usual, we'll be holding a Q&A session at the end, but of course, with so many attendees, a fully interactive Q&A is impossible. We will have about 200 registrations for this session alone. So please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I will address those that I can live at the end of the session, and the rest will address by mail in the coming days. We are recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow, complete with my commentary as well. So double case pumps, when do you need them? Well, primarily when your BB2 pumps run out of puff. That's when you start to need a multi-stage pump. So a BB2 one-stage pump will generate about 500 meters of head at 60 hertz, 300 meters at 50 hertz. There are a few two-stage BB2 pumps out there. It's not a wide range with most manufacturers, including Ruhrpumpen, and they run out of head at about 600 meters or 800 meters at 60 hertz. Once you get above that, you need a multi-stage pump. And there are four options: BB3, BB4, BB5, and BB6. BB5 and VS6. There's also another option, which is the integrally geared pump, OH6, the Sundyne pump. Let's look briefly at all of those. First, the BB4, the ring section, tie bolt design, not fully compliant with API 610, but it is frequently used for boiler feed and desalination feed services. It's a good, inexpensive, high efficiency design ideal for non-process applications. Typical ranges would be about 1,500 cubic meters an hour or 6,600 gallons a minute, at pressures up to about 3,700 meters, which is 12,000 feet. Your next option is a BB3. Now, BB3s have a limitation imposed by API 610 on the temperature, pressure, and specific gravity. But as I say here, don't let that necessarily stop you choosing them. This is what API 610 says about BB3s. It says, unless otherwise specified, pumps with radially split casings are required in services whenever the pumping temperature is 400 Fahrenheit or higher, for liquids with a relative density of less than 0.7, and for liquids with a discharge gauge pressure above 1450 psi. Note that it's not a combination of A and B and C that lead to this radially split requirement. Any of these three triggers the requirement. Now, the specific gravity of less than 0.7 requirement means any ethane, propane, or butane pump at high pressure would need to be a double case pump. But there is an important rider. The fifth bullet here says, axially split casing pumps have been used successfully beyond the limits given above, generally for off-plot applications at higher pressure or lower relative density. The success of such applications depends on the margin between design pressure and rated pressure. This is a key point. The manufacturer's experience with similar applications and the design and manufacture of the split joint and the user's ability to correctly remake the split joint in the field. You should take these into account before specifying one. I will just refer you now to an excellent article by Simon Bradshaw, the pump guru. Well, actually, I know I'm the pump guru, but Simon Bradshaw's pretty good. And he's written an excellent article in his series of things that API 610 got wrong on this particular subject. So follow that link later on. So multi-stage pumps type BB3 shown with back-to-back impellers, half facing one way and half facing the other. So the flow comes in through the suction nozzle, which is around here somewhere on the far side of the pump, into the first stage, into the second, third, fourth, fifth. Then it goes into this crossover and back the other way and discharges here. The back-to-back impellers balance the thrust, so you just have lightly loaded thrust bearings. Here is the joint that API 610 is worried about, the flat joint between top and bottom casing. It worries about the sealing there with light hydrocarbon fluids. Now, note how this design has interstage bolting, often called double row bolting, but I prefer the term interstage bolting. What it does is ensures gasket compression in this area to prevent washover between the stages, particularly at the center bushing here, where the delta P is at its greatest. Here's an example of washover erosion on a pump which does not have interstage bolting. Now, Ruhrpumpen isn't unique in having this design. Flowserve does it similarly, and I recall from my days with Flowserve pointing out to customers how many pumps we had in propane and butane service. I won't spend too long on this. It duplicates a little of what I covered in session 30, selecting the right pump for the application. But here are 2 or 3 slides on BB3s. Ruhrpumpen has 2 designs. For lower flows, it has a diffuser type, JTN. And for higher flows, it has a double volute type, the SM. So here's the diffuser model, the JTN. You see here the diffusers all stacked up here inside the outer case. And here is its range chart for the smaller, lower head sizes. Goes up to about 2,000 gallons a minute at about 3,000 feet head at 60 hertz. And this is the larger SM, the double volute design. And here it's range chart, about 6,000 gallons a minute at about 6,000 feet of head. Now, this range is typical of other manufacturers as well, not just Ruhrpumpen. It gives you the idea of what the range can be for these pumps. Now, of course, light hydrocarbons, C2, C3, C4, they're likely to have a high vapor pressure and low NPSH available. So you may well need a VS6 pump anyway, and VS6 is an API compliant pump. Traditionally used when you have very low, even zero NPSH available at grade. And it works on the basis that if you have 0 meters NPSH available at grade, then 3 meters down, 10 feet down, you have 3 meters of NPSH available. So we make the pump long enough by putting in spool pieces as necessary here to position the first stage impeller low enough to give you sufficient NPSH margin. So it might be 3 meters long, it might be 6 meters long, it could be 9 meters long. But it's not just an NPSH saver, it's a space saver too. 20% of the floor space of the equivalent BB2 or BB3. And it's a cost saver too. It's less expensive than the equivalent BB2 or BB3, and it only has one seal, one sealing system, rather than a BB2 or BB3, which would of course have 2 seals and 2 sealing systems. But here's the problem. Most civil engineers don't like digging holes, which is surprising to me because that's what civil engineers are trained how to do. But, you know, there can be good reasons, such as high water tables or groundwater quality. And if you can persuade the civil engineers to dig a hole, then you could be saving all the way. Big users for these pumps, of course, light hydrocarbons, C2, C3, C4, condensate water in power stations, ammonia, and cryogenic applications, liquid oxygen, liquid nitrogen. Here's a range chart for the semi-engineered or modularized range. The price list pump, you might say, goes out to about 5,000 gallons a minute at about 4,000 feet of head. That's the standard range. Engineered versions are also available at higher pressures and higher flows. Now for low flows, the OH6 integrally geared high-speed pump is popular with some users. It's the Sundyne pump. Here it is with the gearbox here, integral gearbox, self-contained lubrication system, easy to change spin-on, spin-off, automotive-style filter, a Barsky type high-pressure impeller, high-head impeller, and of course an inducer. You're always going to need an inducer with these pumps because they can run up to 22,000 RPM. So you can imagine what that does to the NPSH required. Here is their range chart, and the red circle is their niche market. They have no serious competition in this area. Flows are just too low for a BB5, a horizontal double suction pump, and a VS6 will have just too many stages, 20 or 30 stages to be a viable option. End users either love them or hate them according to their experience. EPCs often hate them because they don't fit into most pump specs, including API 610 and API 682. They have lots of comments and clarifications, but it is a fit-for-purpose pump and fills a very important niche. So here we are, 15 minutes into the presentation, and we finally get around to BB5s. Used when you have no other choice. High pressure, low SG, high temperature. Now again, most of this is generic, not specific to Ruhrpumpen. So we're talking here about a radially split, horizontal, multi-stage centrifugal pump. It's centerline mounted. Yep. Most commonly, it's a diffuser type, but some manufacturers have a volute type, and we'll look at both. Can have a single or a double suction first stage impeller. According to your NPSH availability, you might need a double suction first stage. Most commonly, a top nozzle arrangement, but you can have other alternative arrangements, side or side top. I've even had a question from this morning asking if we could do it at 45 degrees. And yes, there's no reason why it couldn't be at 45 degrees. Thrust compensation on the larger ones would be with a balance drum, or on smaller ones, it's with a rotor design with opposed impellers. Speeds up to 6,000 RPM, and these are the typical applications. Here is a range chart. This is the Ruhrpumpen range chart and covers the more standard or usual range, if anything can be considered to be standard or usual for this type of pump. It's very similar to the Sulzer, SPX and FlowServe range charts. So as you see, it goes out to about 6,000 gallons a minute at heads up to about 13,000 feet. Of course, we all have built to order specials that are out here somewhere or up here somewhere. But this is the general range for most manufacturers. Here we see the outer case, which may be a casting or a forging. There are three different outer casing constructions, which I'll come to in a minute. Top nozzle configuration is most common, but as I mentioned a minute ago, can be side or side top. The inner casing here may be axially split volute type, or more commonly, radially split diffuser type. And the impellers can be either in line, all facing the same direction, that means, or as shown here, back to back. So let me show you the flow. It comes in here at the suction, into the first stage, out into the second, into the third. From that one, it comes into this crossover, back here into the fourth, fifth, sixth, seventh on this 7-stage pump, and out of the discharge here. Now this slide shows ball type bearings. They can be hydrodynamic type, sleeve and tilting pad, which might be required on larger pumps. And these would require a separate lube oil system. Here is the balance line, which equalizes the seal chamber pressures. It also acts as a drain line for the low pressure areas of the pump. Now here is the non-drive end cover. You release these bolts and you can pull out the inner assembly, the cartridge, in this direction. Now, the previous slide showed the more common diffuser type construction. Here we see the less common volute design. You can think of it like a split case BB3 pump inside an outer casing. It's less frequently seen. It's a bigger, heavier pump than the diffuser design because the volute case is bigger. The advantage of the volute design is in abrasive surface, has a thicker inner case and wider flow passages than the diffuser design. And also from a point of view of maintenance, although both designs, both the volute design and the diffuser design, require that the inner cartridge be removed and taken back to the workshop for disassembly. Once you get it there, you can remove the uppercase half of a volute design and remove the rotor as a complete assembly. Advantages of the diffuser design: lower inner casing mass and wall thickness, together with more symmetry, means less warm-up time required in high temperature service. It's lighter and less expensive. And in diffuser designs, the multiple diffuser channels effectively balance the radial loads. You've got six or eight diffusers, as opposed to two diffusers, two volutes in the double volute design. So intrinsically, the balance is tighter. In the diffuser designs, it's simple to provide blank or dummy stages to allow easy change out for future conditions. We could insert a dummy stage in a 10-stage pump, for example, so you have 8 stages now, but can retrofit 2 more stages in the future, for example. Diffuser design allows replacement of individual stage pieces as wear occurs, rather than having to replace the entire inner volute. And similarly, future duty conditions can be achieved by changing the hydraulic combination of the impeller and diffuser. We have impeller combinations, the A, B, and C hydraulic. Well, we can replace impellers and diffusers inside an existing barrel. Now, I mentioned a minute ago, you'll see 3 different outer casing designs. Here are the 2 most common. First one is the integrated cover design, the complete pull-out design. Sorry, the first one is the complete pull-out design. The second one will be the integrated cover design. So first, the complete pull-out design, which is the cartridge having a separate drive end cover, like this. Here we see the cover forging here is a separate forging or casting from the outer case. Is the outer case, and here the cover forging with O-rings, with an O-ring there to seal it. So with this design, it's a complete pull-out design. The whole cartridge assembly, including the bearing housing, can be pulled out. Once we remove these bolts, the whole inner casing can be pulled out in that direction, like that. No disassembly required. Now, maintenance engineers prefer this solution as it minimizes the number of loose parts to be tracked and handled. The second type is the integrated cover design, the heavy-duty casing with an integral suction cover. So here you see the drive end, the suction cover, is integrated into the barrel casting or forging instead of being a separate piece. Just look at the other one again. There you saw it's a separate casting held in place with an O-ring there. And here you see it is all one piece. Design engineers prefer this design as it's a more rugged, robust design. It also doesn't require an O-ring seal on the drive end. It's still a pull-out design, but you do have to remove the drive end bearing housing and mechanical seal cartridge. Then the inner casing pulls out like this. So we removed the bearing housing, and that's why maintenance engineers don't like it, because that can get lost. Whereas design engineers like the greater rigidity of this design. Let's talk about thrust for a minute. I keep going on about opposed impellers, inline impellers, balanced thrust. So what is thrust, and why do pump designers need to worry about it? Well, here is a simple OH2 process pump. Here's the suction, here's the impeller, here's the discharge. You'll see case and impeller wearings here on the suction eye side and on the back side. You have suction pressure acting on the suction eye surfaces. You have discharge pressure acting on these areas, shown in blue here. Now, most impellers have balance holes drilled back to the suction side of the impeller. Here they are. Without these balance holes, you would see discharge pressure acting on the whole of the back face of the impeller and a considerable net thrust towards the suction. But with these balance holes, you get a pressure breakdown across the wear rings and back through the balance hole. And one of the great skills of the hydraulic engineer is designing these balance holes to give the right amount of pressure breakdown without disturbing the flow of fluid into the eye of the impeller, and thus impacting the NPSH performance. So with the balance holes, we have an intermediate pressure here in green, resulting in a manageable amount of thrust towards the suction of the pump. Now, with a single stage pump like this, the thrust can usually be accommodated by an angular contact thrust bearing. But in a multi-stage pump with, say, 10 impellers, that thrust can be considerable. So now let's talk briefly about back-to-back arrangement. Half the impellers face one way, half the impellers face the other way, thus balancing the thrust. So we don't need balance holes if we have an opposed impellers. The thrust is intrinsically balanced. I just have to show you this next slide to illustrate the principle. I love this one. Here we go with impeller in tandem, in other words, inline impellers. Everyone's pulling in the same direction. But if we have back to back, the axial thrust, 3 in one way, 3 the other, it's balanced. It ain't going anywhere. Big thanks here to Kirit Domadia, who posted this one. I've stolen it. Well, this means that because the thrust is balanced, we can use a ball bearing to cover the residual thrust, even on quite large pumps, thus obviating the need for a force feed separate lube oil system. Designs with inline impellers facing in the same direction, they have higher residual thrust, which has to be balanced out with a balance drum and often will require a hydrodynamic tilting pad type thrust bearing and a force feed lube system. Inline impellers are most commonly seen on smaller pumps, where the thrusts are not so great. Here is the balance line. It balances the 2 mechanical seal chambers so they have the same pressure and can have the same seals, except of course that one is in a counterclockwise direction and one a clockwise direction. We have an integral flange on the case casting, and it's a butt welded full penetration welds construction in the balance line. And here is the drain connection for the low pressure areas of the pump. And here the drain connection, a separate drain connection, again integrally flanged for the high pressure sections. And here they are in this picture, integral flanges. And here the balance line. Now we'll move on to sealing of the barrel. There are 2 ways. It can be axially sealed, as shown here, and the other will be radially sealed. So first, axially sealed, what we have is an O-ring on a high, it's a metallic O-ring, stainless steel, grade 321 or Inconel X750 for corrosive applications. It's a confined O-ring held in place there by the high pressure bolting here. So it offers superior sealing ability because it's under compression and tension. Compression by the clamping force of the bolting, and tension because we drill small holes in the inner face of the inner diameter of the O-ring, allowing high pressure liquid to enter that area, and so that pushes outward while the bolts are pushing it inward. So it requires low clamping forces. This is the design used for high temperature use, 816 degrees centigrade here, 435 Fahrenheit for you guys. Good advantage because it's an axial seal. We haven't got a radial seal in here, so we don't need a tight fit between the cartridge OD and the barrel ID. So that allows for easier and faster assembly and disassembly, and no hydraulic ram needed. This is the high pressure, high temperature construction. Regular elastomers can be used at lower temperatures and pressures. The other method is radial sealing. And this is the third casing design I mentioned before. It's the Sulzer twist lock design. There's no bolting with this design. You slide the inner case in, it's a radial fit, push it in and twist lock. As I say, no bolting required with this design, which you might think is an advantage, but you cannot use an axial seal, which requires compression from the bolting. Instead, it uses a radial seal. And here is the radial seal. Here we see 3 O-rings supported by anti-extrusion rings, because the high pressure would just squeeze them out of the pump otherwise. It demands accurate levels of concentricity for sealing and perpendicularity. It means we have an interference fit of this casing inside the outer barrel, and means you need a hydraulic ram to install and remove it. Consequently, there's a risk of damage to the O-rings there. Here are some other things to think about with the twist lock radial seal design. High probability of snagging the O-rings on installation and removal. You need anti-extrusion rings, as I mentioned, and these can be, because they're process wetted and vulnerable to localized corrosion, and could make it difficult to remove after prolonged periods of operation. But it's a well-established design, and Sulzer use it quite a lot. The perceived advantage of the twist lock system is you get rid of the bolting, which requires a hydraulic bolt tensioning tool. Well, this is not an issue on a large site, as you'll have them there anyway for compressors, large pumps, gas turbines, and so on. It might be more of an issue on remote areas, remote sites. And then we have this multi-jack bolt tensioning. The coolest thing I've ever seen, I think. Widely called super bolts, but this is in fact the trade name of Nordlock. I have to say, other manufacturers of multi-jack bolt tensioning do exist. What it does, it allows you to tighten the bolting using conventional hand tools instead of requiring a hydraulic bolt tensioning tool. You tighten the nut by tightening each of these jack bolts in turn using conventional hand tools. You can also buy a super bolt tool to make it even easier. Tightens all 8 jack bolts at the same time with conventional tools inserted in here. And here is a link to a video to see how this works. I'm not going to run it now. It runs for about 10 minutes. So look at it at your leisure. Moving on from the casing, let's take a look at the rotor. We see here a stepped shaft with each impeller located by split rings and a shouldered fit to make sure it cannot move axially, and it thus distributes the forces equally along the shaft. The impellers are a medium fit, so somewhere between clearance and interference. It's a tight fit on here without needing to heat it up to slide it on. Three bearing cooling options. We're showing here anti-friction bearings, which are used on most pumps. Of course, we also have hydrodynamic bearings, sleeve and tilting pad bearings, which are used on larger and high-speed pumps. For these ball bearings, they come with air-cooled, fan-cooled, or water-cooled, according to the temperature of your pumpage. This is the balance drum that is required for inline impellers. You might have 10 impellers lined up here, so you've got full discharge pressure acting at this point here. You've got suction pressure acting at this point, and across this labyrinth is the pressure breakdown. It balances 85 to 95% of the generated thrust, and the residual thrust is handled by a thrust bearing. Here. No axial movement, but the leakage increases with wear, leading to an efficiency drop and an increase in thrust. As I say, it only balances 85 to 90%, so on smaller pumps you'll need an angular contact thrust bearing, which can be ring oil lubricated to take that residual thrust. Or on larger pumps, or when specified, when there's higher thrusts, you have hydrodynamic tilting pad bearings, which will of course require a force feed lube system, maybe to API 610, maybe API 614. This is the tilting pad pivot shoe hydrodynamic bearing, the Kingsbury type bearing. It's used on larger pumps and higher speed pumps, and of course on inline rotor designs where the thrust loads are higher. And it depends on a film of oil holding between the runner and the tilting pad. The tilting pad tilts, pivots to maintain this oil film. Just want to revisit the inner cartridge removal process. It uses a special mounting tool shown here in red. This is obviously the Ruhrpumpen design. Each manufacturer will have a slightly different design. This is the complete cartridge design. And here we see it with the integrated cover design, where you remove the drive end bearing housing and seal first, and put it down where it won't get lost, and then remove the cartridge like this. And here are some photos of the tool and removing the inner cartridge from the case. This is taken at one of our service shops. This pump coming out for service. So it's a clearance fit in here, so you don't need a hydraulic ram. You can just slide it in. No O-rings to worry about. No radial O-rings here to worry about as you insert it in. So these double case pumps are very much engineered pumps. Specialist for pumping technology has long been our byword. German engineering throughout, using the latest engineering tools. So finite element analysis and computational fluid dynamics, as well as by doing rotordynamic analysis on every rotor. And of course, we're not unique in this design. Flowser, Sulzer, SPX will all be offering these service. They make high quality pumps too. I now have about 15 slides of barrel pumps. I guess this is the product placement part of the presentation. Those who tuned in early will have seen some of these already. I'll go through them fairly quickly so as not to bore you and also allow time for the Q&A. This one, the Statoil Valamon platform, a very congested skid, which is typical on an offshore installation where space is at a premium. Here is a pump on string test, all the contract equipment being used, the job motor, lube oil system, the pump, the gearbox, and instrumentation. Very big unit here, 5,200 kilowatts, 4,200 RPM. The Ruhrpumpen test bay can test up to 6.5 megawatts. If we need higher, there's the Siemens facility at Duisburg just down the road, which has a 17 megawatt capability, so for the largest pumps. And I put this slide in to illustrate the type of base plate that is often required for offshore work with a 3-point mount base plate. Well, that's it for today's session, apart from the Q&A in a moment or two. But first off, I just want to advertise the next of these short courses. 30th of January, 2 courses, one in the morning for the Eastern Hemisphere and one in the afternoon, my time, for the Western Hemisphere. That's you guys. The invitation will be published very soon, and it's going to be on startup, commissioning, and troubleshooting of centrifugal pumps. And that'll be the last one for the year. Well, it'll be the first one of next year, in fact, won't it? After that, well, what would you like us to cover? Let me know, give me your suggestions, and I'll see if I can't write one for that. Well, I'm leaving the meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer, here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, email to marketing@ruhrpumpen.com or to me directly, smith@ruhrpumpen.com. Our marketing team will send you the YouTube recording, the PDF of the presentation, and the consolidated Q&A from both of today's sessions. If you need a certificate of completion for this short course, again, send an email to marketing@ruhrpumpen.com and they'll sort you out. And here, right at the end, are 8 slides about Ruhrpumpen to remind you of who we are and what we do. They'll be in the PDF copy of your presentation that you get, so you can peruse them at your leisure. And now, on with the Q&A. Stop the share, and let's have a look and see if we have any questions. We have 10 so far, I think. The anonymous attendee has said, please share Ruhrpumpen's experience with dense phase CO2 at around 2,400 psi inlet and 5,000 psi discharge. Okay, I can't answer you that one straight away, but I will get a good answer for you and put it in the combined written answers. Jeroen Boller says, do you have any experience with pitot tube type pumps for low flow, high head applications? Yes, we have some pitot tube pumps. It could be considered as an alternative to the OH6 pump, if you like. it might be a good idea to consider doing a presentation on those pitot tube pumps. There's something completely out of the ordinary. Not many people know about them, in fact. Yeah, I'll write that one down for the future. But we do have a pitot type. We call it the combi tube, and yeah, it's good for about up to about 50, 60 cubic meters an hour, and pretty high heads. I can't remember exactly, but it is good for that in clean service. Nalathambi Dharmalingam says, please clarify the criteria for selection criteria for opposed impeller and balance drum in terms of head or flow. This would be the job of the applications engineer to look at. If it's a low flow, if it's a fairly small pump, we could consider going with the inline impellers. If the residual thrust is going to keep it inside the requirements of an angular contact ball bearing. Once you start getting to needing a tilting pad bearing, the price starts going up and it becomes much more worthwhile to go with opposed impellers. So it's just a value judgment. We'd make that decision on a case-by-case basis, depending on the process conditions. Nanathambi Dharmalingam says, what's the maximum impellers available for BB5? How a number of impellers are decided during pump selection? Well, we optimize it. Ideally, we'll have impellers that are about 95% of their full diameter operating, and so that will determine how many stages we need. We have gone up to 16 or 18 stages, I believe. Commonly, it'll be 8 or 10. Some customer specifications say no more than 10. There's no good reason for them saying that. They just don't like the idea of too many stages. Anonymous attendee says, if you have dummy impellers in a pump, does it create thrust-bearing problems that need to be considered? No, because it would have been designed in that case. We don't actually put dummy impellers. What we will do is take out, say, 2 impellers and put a spacer of the same dimension in there instead. So the flow goes directly from one impeller to the next one. So no, is the short answer. Anonymous attendee says, please explain the difference in mechanical seals for clockwise and counterclockwise direction for the 2 sides of the pump. They'll be almost identical. It's just the pumping ring will be designed to operate in the opposite direction. Anonymous attendee, a lot of those today. In the future, could you make presentation about the lateral and torsional analysis? When are they required? How are they performed? And how to review them? Thank you. That's an interesting thought. My initial reaction is that it's rather a specialist field for these very general courses. But let me think about it. And if I can do a lateral and torsional analysis for dummies type presentation, by dummies, I mean me, then I'll try and see if I can do one. The anonymous attendee again, which one is a costly design, a volute type or diffuser design? Generally, the diffuser design will be less expensive because it is lighter and has less material in the casing. Nalathambi Dharmalingam says, these pumps are recommended to test job motor or shop motor during performance test. Well, because they're likely to be pumping a lighter hydrocarbon, less than SG of 1, but we'll be testing them on water. So it's usual to test with a test job motor. If you've got the motor sized suitably that it can be used, no reason why we can't use the job motor. It will have been fully performance tested at the manufacturer, so we'll have a calibration curve so that we can use that motor for doing the performance test for the pump. Damesh Kuna Panchal says, maximum speed limit of BB5 pumps for 10 stage. Practically no limit. I mean, we can do them at 6,000 RPM as necessary. These are engineered special pumps, remember. So we're doing a torsional and critical speed analysis on every pump. It will be designed for that service. Zinedine says, for which power do we need a hydraulic tilting pad? No easy answer. The application engineer will work it out on each case. Yeah. Anonymous attendee has said, how can one prepare themselves for hydraulic and mechanical design of BB5s? Not quite sure what you mean here. How can one prepare themselves for hydraulic and mechanical design of BB5s? At the very early stage, if you're a process and mechanical engineer at an EPC or end user, for example, get the pump manufacturers involved at a very early stage. Give them your preliminary duties, process conditions, and they will give you their recommendations from a very early stage at the early design stages, so you know whether you're going to need a double case pump or a single case pump, whether you're going to need force feed lube systems. All this can be sorted out at a fairly early stage as soon as you get your preliminary process conditions. Victor Mihangos says there are two types of balancing thrust devices, the thrust drum and the disc. Would you please explain how each of these work and how is the balance calculated and or managed? Can't do that easily. First, let's say the first thing. There's a thrust disc and a thrust drum. API 610 only allows you to have a thrust drum. It won't allow you to have a thrust disc. Thrust disc is often used in BB4 pumps that are on clean applications such as water injection or power station use. Yeah, boiler feed. That's what I'm looking for. Boiler feed pumps can use them. Clean pumpage. I did a presentation on BB4 pumps a few weeks ago. You might like to look that one up because I do go into thrust balanced drums and balanced discs in that one. It's a little difficult for me to just discuss that now without prepared slides. So sorry, Victor. I'll see if I can't give you a better answer in my written replies. The anonymous attendee, could you explain the difference between the axial and the radial gasket again? I'd like to come back to that one, actually. I don't want to hold up the Q&A. I've still got several more Q&As. If I've got time in a minute, I'll go back into the show and show it again. Victor Mihangos says, what is the ratio between the length of the assembly and the pump shaft diameter? The effect of weight on the rigidity of the shaft and assembly? How to store a spare volute to avoid sagging effect? Okay, I'll take these one at a time. What's the ratio between the length of the assembly and the pump shaft diameter? That's not a published figure. What you're getting to here is a long shaft will tend to do this, and that's fine. And it might at the center bushing, it might touch at that point. As soon as you start the pump, Lomakin effect will make it rise up off there. And that's one of the things that we're looking carefully at during the design of the pump. So that's the effect of the weight on the rigidity of the shaft assembly. How do you store a spare volute to avoid the sagging effect? It's quite common for people to specify that it be stored in a vertical situation. We have successfully stored them for years in a horizontal version. It's not a bad idea every now and then to open the case and rotate them to stop any permanent deformation. How long can the spare volute assembly be stored and be reliable for use? For a long time is the short answer. Is there any test to perform prior to installing a pump or spare that has been on the shelf for some 4 to 5 years? I'll get some advice from product specialists on this. You've asked some very interesting questions here, Victor, and you deserve a considered answer on them. So thank you for that question. Anonymous attendee has said, VFD versus fluid coupling, which one is best technically and cost-wise? VFDs have come on leaps and bounds. I would have said, 20 years ago, the fluid coupling was ubiquitous, just about everywhere. Nobody would use a high tension VFD, but say VFDs have come on leaps and bounds, and you can now buy good, reliable, not too expensive VFDs for high voltage motors. But it is a balancing act, really, and I would always look to consider both the fluid coupling and the VFD for any application. Damesh Kumar Panchal, what is the Lomakin effect? Another day, I'm afraid, another day. Anonymous attendee again. Can the pump be assembled vertically due to space constraints? I don't know. I don't think so. One for my product experts, I'm afraid. Okay. I still have 60 of you online. Let me see if I can go back and here we go. The axial and radial split. Okay, here's the axial split. So what we have an O-ring here in between the cover and the case. And these bolts here compress it and hold it in place. So that's the sealing area there, okay? What we also do is we drill holes in the inside of this O-ring so that the process fluid pressurizes in there and starts pushing outwards. So we have compression from the bolting and we have process fluid pushing outwards so that we have it simultaneously under compression and tension and requires therefore low clamping forces. That is the primary seal. Therefore, this casing, inner casing, doesn't need to be a tight fit inside the outer casing. It can be a slide fit in there. With the twist lock design, we no longer have these bolting, so we can't have this O-ring here. Instead, we rely on radial sealing there. So here we go. Either end of the pump, we've got this arrangement of O-rings, which seal between here and the outer case. And it's an interference fit, basically. It's a tight fit. We have to have anti-extrusion rings to stop the O-rings pushing out through the, squeezing out through the gap. So this whole thing is an interference fit within the barrel, and it needs a hydraulic ram to install or remove. I hope that was clear. Just go back to the Q&A. How reliable is the twist lock design, says an anonymous attendee. Sulzer swear by it, and they are a very reputable company. So I wouldn't say it's no good. Ruhrpumpen have decided not to go down that line. We prefer the axial seal, but no, I wouldn't poo-poo the Sulzer design. It's still a good design. One of my product experts has come back to me on the vertical assembly. He says, in general, the footprint of this vertically with the large support doghouse to theoretically support it would be about as large as the horizontal footprint. But if you can emphasize, if there are space constraints, we can work to minimize our skid dimensions. Yeah, it's an engineered pump. We are working with you to do the best for me. And if it's an offshore platform and you've got very little room, we're looking to minimize the size. That's when we'll be going to high-speed pumps instead of regular synchronous speed motors, for example, all trying to get the footprint down as much as possible. And that would appear to be all the questions I can see here at the moment. I'll just check in the chat and see if anybody put anything in there. No, they didn't. So it just remains for me to say thank you again for attending today. I enjoyed preparing it and presenting it. I hope you found it useful. see you on the 30th of January, which is in 6 weeks' time, for the next short course, by which time I'm hoping that one of my family will have bought me a new waistcoat and tie combo to wear, so I don't have to wear the same old ones again and again. So Merry Christmas and Happy New Year. This is still a cup of tea, but it's beer o'clock, so I'll be unstopping one now. So thank you very much again, guys, and bye-bye.